let's get this show on the road. Hello, everyone. Hope you're well. Let's get into it. As Kayla said, let's get this spread. Time is of the essence. You guys have, I mean, I know it seems sudden, but it is the summer. What can you expect? You guys have your first test like next week. So let's actually get a move on so that we have a good, as much time as possible to actually get things through the way. Yeah, I know, right? Very surprising. Anyway, let's actually just jump into it. So last time we spoke about improper integrals and the convergence, the comparison theorems, sorry. So improper integrals, those are just integrals, as you may recall. Where was this? Improper integrals, those are integrals that did not fit in with the whole fundamental theorem of calculus idea. So our function was either undefined at finitely many points on the interval AB, or the interval was infinite in some sense, like the upper limit was infinity and or the lower limit was minus infinity. We figured out that we could compute those using limits. We also saw that there were some situations where even this method couldn't help us figure things out. So this theorem came in handy when coupled with the comparison theorems. This allows us to talk about whether or not an improper integral converges by comparing it to some other integral that we know for sure converges. So that's important. But now we're going to deal with the question, what if we do want to get a little bit more specific with our integrals? We want to, it's very hard to compute the integral. However, I would like to get reasonably close to the answer, right? That leads us to the topic of today's discussion, numerical integration, which we are covering on the 17th. Okay. Now, numerical integration, as I said, comes in handy when you really want to try to figure out what an integral is, especially a definite integral. No. So yeah, someone already brought that up to me, by the way, that some of the chapter 10 sections are due on Sunday. No, that's not a mistake. You never know how the class is going to go. So those are deadlines that I set at the beginning of the semester. I'll push those. I'll push those when we're done. Yeah. So I'll push all deadlines so that, you know, the homework is going to be due after we actually cover the topics in class. We should be starting chapter 10 today. So we'll see how far we get. Okay, so sometimes we actually want to compute definite integrals, and it's not even that they're improper. So for example, this integral here is not improper. This one here is not improper either. However, we can't integrate those guys. So we want to be able to deal with integration like that. Since we can't actually compute them directly because we do not have antiderivatives for these guys in terms of the elementary functions, we are going to do the next best thing, which is approximate them. Now, some of you might be rocking nervously in your chair at this point, having bad memories from elementary school where the math teacher is like, no, you have to get the exact answer or it's wrong. And you're like, oh no, I can't put a radical in the denominator and the answer has to look just like this. It turns out, kids, in real life, sometimes getting to the exact answer or getting to a nice form of the answer, this is what we call a closed form, quote unquote, is just not possible. We cannot do it. What we can do, however, is we can approximate answers. And believe it or not, most of the time this is what's happening, and most of the time this is only the thing that's needed. A lot of the times, even if we have an exact answer, it's not going to be useful. Like we can't even use the exact answer even if we had it, right? So if you did some calculations, you're an engineer, you're a civil engineer, you're doing some calculations and you got to the exact answer. Okay, we need pi tons of concrete to build this thing. Oh, good luck finding pi tons of concrete. How are you actually going to do that? Pi is a non-repeating decimal that goes on forever. What machinery are you going to have that is going to be accurate enough to measure pi tons of concrete? You can't do it. Every instantiation of pi we've ever seen in our lives has been an approximation. We know pi up to a certain number of decimal places. Whether using Mathematica or Wolfram Alpha or Symbol Lab, it only uses pi to a certain amount of decimal places. So if your answer, the real answer is pi, it's actually not even usable in the real world. At the end of the day, you're going to simplify it to like 3.142 or 3.14159 or whatever, right? You're going to approximate it. So don't let approximation feel like a cop-out. A huge part of math is about how do we approximate things efficiently? And how can we approximate things in such a way that we can tell exactly how good our approximation is? Because a lot of the times, approximation is the best we can do. And a lot of the times, approximation is the only answer that's actually usable anyway. So that's what we're going to do. We can't compute these integrals, so we're going to learn to approximate them. How do we approximate them? Well, we go back to first principles. You might recall back in Calc 1, we learned several methods to actually compute an integral. Back before we learned about the fundamental theorem of calculus and that we could use antiderivatives to compute integrals, the integral just meant the area under the curve. And we had certain rules that can try to measure the area under the curves. Specifically, we had the idea of using what's called a Riemann sum. And we learned 3 flavors of this guy. So one was the left-hand rule. So this was when you had a curve, you care about the area under that curve between A and B. And what you did was you dissected that interval into what you call subintervals. And on each of these intervals, what you did was you erected rectangles. And in the left-hand rule, you let the left side of the interval define the height of the rectangle. So here the left side defines the height of the rectangle. The left side defines the height of the rectangle. The left side defines the height of the rectangle. And then the sum of the areas of these rectangles was used an approximation for the sum of the areas for the area under the curve. Similarly, we had the midpoint rule. So you can use the same guy here. Let's say you care about finding the area between A and B. Yeah, what you did was you found some subintervals. For the midpoint rule, you took the middle of those intervals and you let that define the height. So you take the middle, you let that define the height, to the middle, let that define the height, to the middle, let that define the height. And then you erected rectangles that had that as the height on each subinterval. Right, so it goes across there, cuts across there, cuts across there, right? And again, you summed the area of these rectangles and that was your approximation for the area under the curve. The right-hand rule, same idea. So we had this curve doing its thing. We want to find the area between A and B under this curve. What we do is we dissected these things into subintervals. For the right-hand rule, we let the right side of the subinterval define the height. The right side defines the height. The right side defines the height. The right side defines the height. And again, so by adding up the areas under these rectangles, we got an approximation for the area under the curve. And we saw that the more rectangles we used, the better the approximation was. So if the area was just, if in this case, you can see that the left-hand rule would give us an overestimate because the function is decreasing. If we didn't like how much that the overestimation was too big for our taste, just use more rectangles. We also had the idea that the length of each subinterval was a guy that we called delta x, and we knew how to find those. Delta x was equal to b minus a over n, where n equals the number of subintervals. This is going to be true even now. So this still will be used in this section. So remember that. It's something that was defined for you in an earlier class, but it is an equation that I do expect you to still remember, the fact that delta x is b minus a over n, right? So this was an idea, right? This is how we were computing integrals before, right? And we could write this as a Riemann sum, and then if we set this up for some general n and then took the limit as n approaches infinity, this gave us what we call the definite integral. And we had the integral sign from a to b of f of x dx to represent that. The integral sign there, of course, is an elongated s, which just stood for sum, the sum of the areas of these rectangles. That's where the integration symbol idea came from. Okay, so we've all been here, right? So what? Oh, sorry, my cell phone was ringing. So what were do I want to talk about overestimates and underestimates? Yes. So overestimates and underestimates were a big deal here. Notice above the left hand gave an overestimate, while the right hand gave an underestimate. I was going to draw some pictures here, but I can't be bothered again. Okay, so above here, notice that the area of the rectangles would be larger than actual area under the curve, while for the right, the area of the rectangles would be actually smaller than the area under the curve. The midpoint kind of tries to do a give and take. The midpoint, it's hard to tell whether it's an overestimate or underestimate. But it tried to minimize the error. Via like a give and take, right? So that's the situation here. For the midpoint, notice that on one side, it's an underestimate, but then it kind of tries to make up for that on the other side by giving an overestimate. So hopefully it's hoping that its underestimate and overestimate kind of balances out and would give you a more better approximation sooner. Okay. Now here's the other thing. We can do either of these, and for us it wasn't really a big deal because normally when we are asked to use one of these methods to approximate the area under this curve, the question is going to be something like use 4 rectangles or use 3 rectangles or use 5 subintervals. It was never really a lot because you were doing it by hand. However, when a computer is trying to approximate an integral, it's going to use thousands of subintervals, hundreds of thousands of subintervals if it needs to, right? Now, when you start to do that, go into hundreds of thousands of subintervals, millions of subintervals, it turns out starting to add up all of these guys results in a lot of computation time, a lot of computational power, a lot of computational effort. Therefore, we are going to want to be more efficient. And what we're going to cover in today's class is 2 other methods that do exactly the same that the left, right-hand, and midpoint rule does. However, they're potentially more efficient, especially when you're going off to larger and larger number of subintervals. So that's what we're going to do. We're going to
This
use
would be the trapezoid rule and and also the midpoint rule and the Simpsons rule.
Right. Midpoint rule you already covered in Calc 1, but yes, we're going to do the other 2. We're going to do the trapezoid rule and something called Simpsons.
The Simpsons rule.
So first, we need to review the area of trapezoid. We need to remember how to do that. Okay. So where this rule comes from is coming from the area of a trapezoid. The idea here is that on the subinterval, so you have some curve here. Basically, you want to find the area of the curve on between A and B. The idea is, yeah, the same thing, set up our subintervals as we did before, but this time instead, what we're going to do is not use rectangles at all. We're going to use trapezoids. So how we create these trapezoids is we can take where the endpoints meet the curve and connect those with a straight line. Take where the endpoints meet the curve, connect with a straight line, take where the endpoint meets the curve, connect with a straight line, takes the endpoint meets the curves, connect with a straight line, and so on. So now you'll notice here, when I erect these trapezoids, the straight lines will fit closer to the curve than just an ordinary rectangle would. Now, of course, it's not going to be perfect, right? You'll notice that we're still missing a little bit here, but the idea is compared to how a horizontally flat top would look, the trapezoid seems to hug the curves a little bit nicer. And so in theory, we should be able to get to a better approximation for the answer with less subintervals, right? Because these subintervals don't leave out so many errors to begin with. Now, what we can do is use the area of the trapezoid to actually sum up all these areas and come up with a formula for this. So notice here, the area of a trapezoid is half the sum of the two parallel sides times the distance between the two parallel sides, right? So that is the area of a trapezoid. So we can actually do that here. And I'm going to... Yeah. So I would do that for this one. So let's actually label some things here. Let me call A x naught. Your B is like your xn as usual. Let's say this is y naught. That's the y output. And this is y1, y2, y3, so on. This here would be x1, x2, x3, so on. So the y1 is the output of x1 and so on and so forth. What you can realize now is based on the area of the trapezoids, this here is going to be 1/2 times the length of the two parallel sides, y0 plus y1, times the distance between them, which is the distance across here. Now, the distance across there is, of course, delta x, the same delta x that you had from Calc 1. Okay, and so that's how you would find the area of that one. If you find the area of this one, that would be half of y1 plus y2 times delta x. The area of this one will be 1/2 times y2 plus y3 times delta x. All right, so you can find the area of all of these individually. Now, when you stick a bunch of trapezoids together and sum them together, so here you're going to get the area is going to be the sum of above. So this is going to look like delta x over 2, which is going to be a common term. And then you're going to have y0 plus y1 plus y1 plus y2 plus y2 plus da-da-da, going all the way up to yn. You'd realize that some of these terms are doubling up because the endpoint of this one, the y1 over, the y1 over here, the last guy here is the first guy in the next one. The last guy here is the first guy in the other one. And so what you realize ends up happening is that this becomes delta x over 2 times y0 plus 2y1 plus 2y2 plus 2y3 plus 2yn minus 1 plus the last guy yn is going to be that. So you end up with this sort of formula. So it looks almost like what you would look like a midpoint rule or something. But instead here, all the intermediate guys are doubled. And they're doubled because of the area of a trapezoid formula. And here we have delta x over 2, again, from the area of the trapezoid formula. So this leads us to, drum roll, the trapezoid rule. That's this guy. So the definite integral from a to b of f of x dx is approximately equal to t sub n. This represents the trapezoid approximation with n subintervals, and it's going to look like delta x over 2 plus blah, blah, blah. Here, your xi are just the x values for the subintervals, and it goes without saying, but your delta x is going to be b minus a over n. Now, this is actually a snippet from a PDF of this topic that I have on the class website. So you should also check that out. So I'm putting all of these in a PDF. So that's basically it. Now, I'm going to do some examples later, but let me actually talk about the other one. So that's called the trapezoid rule, right? So it's something that's very similar to the midpoint rule or the left-hand rule or the right-hand rule, but we use trapezoids instead. And what that means is that this formula comes into play. So all the intermediate guys are doubled, but the first y value, which is the y value corresponding to the a, and the last y value corresponding to the x equals b, those guys are not doubled. And we multiply by delta x over 2. Yeah. So that's the trapezoids. Now, here, we are going to use Simpsons rule. Now, Simpsons rule does something else. Simpsons rule actually uses areas under parabolas. So we're going to need to figure out the area under the parabola. So Simpsons rule uses parabolas. Right? So Simpson was like, why are we using anything with a straight edge anyway? I mean, if I have a graph that is wavy, why not look at it with other things that are wavy, like a parabola that comes here, and maybe another parabola that connects and comes here, right? Why not find the area under two parabolas instead of trying to find the area under some straight edge thing, right? So Simpson's just another mathematician. Just a mathematician, right? So Simpson was this guy who came with this other idea. Hey, maybe we can use parabolas instead. So now let's actually figure out how we would use parabolas. How would I find the area under a parabola? The idea is to figure out the area under a parabola, to identify a parabola, I need at least 3 points to identify a parabola, right? You can identify a straight line with 2 points. You need like 3 points to identify a parabola. You'll need like 4 points to identify a cubic, and so on and so forth, for those of you who've seen polynomial interpolation before. Okay, so how do we actually get that done? So there's no high school geometry formula for that. The nicest way to find the area under a parabola will be using calculus, so that's what we're going to do. So let's and I think this picture, the way I described it should be moved under here. Okay. So here's what we're going to do. So let's figure out so usually what we do is we center the parabola around the axes. So imagine that the parabola is like here, and that's the first point. So there are 3 points to worry about. Now, if the parabola is not centered, obviously as it's not in this case, don't worry, we're just going to translate our answer. We can shift it left or right. So we're going to worry about 3 points here. So the first one is like x0, which leaves us with y0. Then here we have x1, which is actually specifically 0, and this is y1. Then here we'd have x2, where the output is y2. And I want to find the area under this parabola. Well, how do we find the area under the parabola? We're going to cheat and we're going to use calculus. We're going to actually use the antiderivative. So pretend the equation for this parabola is ax squared plus bx plus c, right? And we're assuming it's centered so that the vertex is on the y-axis. Of course, we can translate the answer. I keep forgetting where I left space to do the diagrams. Just actually left a space for that here. Yeah. Jhevon last week planned ahead, and Jhevon today totally forgot the plan. Like I was leaving spaces for where I'm gonna put everything, but like I'm just going now. I'm just in the zone, and it's like, oh yeah, I forgot everything, like the structure that I had set up. Whatever, we're fine. Okay, now let's do the calculations. So the area is going to be the integral from it's going to be, and I'm also going to call delta x equals h here for no other reason other than it's just easier to write out. So think of this distance as h and this distance here as h. So I can think of my x0 as minus h, and I can think of my x1 as h, just to make it easier to write out. So this is minus h to h of ax squared plus bx plus c dx. This is going to give us ax cubed plus b ax cubed over 3 plus bx squared over 2 plus cx between minus h and h. Now, I'm laughing at Kayla's comment. They get me to lose it. Okay, so we're going to plug in the h. Now, when I subtract and plug in minus h, this guy here is actually going to double up. This guy here will actually get canceled out. And this guy here is going to actually double up. So we just have this. What we're going to do now is I'm going to factor out an h over 3. And you'll see why I decided to factor out an h over 3 momentarily. So we're going to have 2ah squared plus, this would end up being 6c. Okay. Now, here's something we can apply. Now, note the following. This is my parabola, and I know this is the equation of my parabola, and I know how it's situated, so I can actually know a few things about the parabola. For one, well, that's because if I have ah cubed over 3 plus blah, 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 and then I subtract when I plug in minus h plus blah, 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 then ultimately it's going to be ah cubed over 3 minus h cubed is just minus ah cubed, and then I put that out, it's going to add another ah cubed over 3, which gives me 2ah cubed over 3. So I did the fundamental theorem of calculus in my head just now. So that's where that came from. Anyway, now note the following. I actually know what p of 0 is. This is actually going to be the c value, but I know that this is going to be what I defined as y1, right? From this diagram here. On top of that, I know what p of minus h is going to be. That's actually going to be, if I plug in minus, so my p of x is ax squared plus bx plus c. Now, p of minus h is simply going to be ah squared minus bh plus c. However, that I know is y0. P of h is going to be ah squared plus bh plus c. That I know from my definition is actually y2. I can add these two together, and what I would get is 2ah squared plus 2c equals y0 plus y2. So it turns out that these guys are going to actually be useful. And now you're seeing why this 2ah squared right here is going to be important. So now, here I have h over 3 times 2ah squared plus 2c plus 4c. And this part here is talking about this part here. Right? And if I look over here, I know what C is. C is y1, which means the leftover 4c, I can use that here. So I'm going to use these little side calculations to inform this little guy here. And what's going to happen when I start writing these guys out? The first guy is going to be y0 plus y2. This guy over here is going to be 4y1. So now I end up with this situation. I end up with h over 3 y0 plus 4y1 plus y2. Or to use the old notation, to bring it back, old notation. This is going to look like a delta x over 3 times f of x0 plus 4 f of x1 plus f of x2. So that's the area under a single parabola. I can actually use this formula, believe it or not. And now what we do, putting a bunch of parabolas together. Hi, can you guys hear me? Okay. All right, Fahim, it's probably on your end. It seems everyone else can hear me. Okay, now when you put these guys together, what's going to happen? Well, here's my curve doing its thing. So here's how we're going to do it. Here's from A to B. I'm going to dissect into a bunch of subintervals. Now notice that we're going to need 3 points to define a parabola. So there's going to be like 1, 2, 3, and then the parabola would go through those 3 points. Then define 1, 2, 3, and then there's going to be a second parabola going through those 3 points. Then define 1, 2, 3. There's going to be a third parabola going through those points. Now, one thing I want you to notice, so we're going to find the area of this, the area under this one, and then the area under this one. Notice here that I would always have an even number of subintervals here because I need 2 subintervals to come together for each parabola. So one thing you're going to notice about Simpsons rule is you always need an even number of subintervals. So that's going to come into play. However, what we can now realize is that this guy is going to do something like the area is going to be delta x over 3 times y0 plus 4y1 plus y2. The area under this guy is going to be again delta x over 3. And that guy is going to start at y2 and then 4y3 and then y4. And then this guy is going to be your delta x over 3 times y4 plus 4y5 plus y6 and so on. And so now when you put them together, combine and factor out the delta x over 3, you putting these together, you would get the area is going to be like delta x over 3. You're going to have y0 plus 4y1. The y2 will double up from the 2 parentheses, and that's going to be 2y2. Then you have 4y3 plus 2y4. Then you have 4y5 plus 2 da da da. Notice here, now there's an alternation of 4s and 2s, starting with the second guy. This leads us to Simpsons Rule. Right? So here's the formula. It's delta x over 3 this time. And now you sum all the guys here, like 4 times, you start alternating on the second y value with a 4. Then it goes 4, 2, 4, 2, 4, 2. It stops alternating on the 4 for the second to last term. And then the last guy isn't multiplied by anything, right? And again, here your n is even. That's something you have to remember for Simpsons Rule specifically. You need an even number. And of course, your delta x is the same thing, b minus a over n. Yeah, it's pretty convenient. Yeah, it's a very nice formula. So these are the patterns, right? Now, you don't have to know how to derive them. You just need to know the formulas. Deriving them, though, can make you remember, do I start with the 4 or the 2? That's usually something that students forget. And if you know how it's derived, you will realize, oh, there was a 4 in the middle when we were doing that derivation, and so we start with a 4. So that's going to be Simpsons Rule. Right, now here is something talking about the errors in the approximation. And unfortunately for you guys, we're essentially going to skip this discussion, but just so you know, an approximation is only good if we know how bad it is, essentially. And these guys here tells you how to approximate the errors of the above approximations. So you can actually know exactly how good, down to any decimal place, any number of decimal places you want, how good is the Simpsons approximation? How good is the trapezoid approximation? How good is the midpoint approximation? Now, this is something that I covered with my class in the spring. However, in the summer, with everything being so cramped, I don't really want to cover any optional material with you guys, really. Unless there's like a really, really good reason to cover it, I'm not going to cover it. It's just too squished together. So if you want to watch my lectures from the spring, if you're interested, I actually do go through this with them. But for you guys, I'm going to skip it. So you can do that after the class is over if you want. And a PDF, like I said, of everything that I spoke about here, it's in a PDF on the math department on our math webpage for our class. This is a direct link to that. Now let's go on to some examples. So these guys are also from the PDF. I just took a snippet of them. We're going to go through these guys so you can actually see how to actually apply this. And it's a lot less complicated than you might think. So what am I looking for? It's big enough for that. So let's go on to some examples. So we are going to ignore any problem asking for errors. Again, that's because it's the summer. And we'll also ignore, by the way, so for us, more specifically for us, only need to know Trapezoid Rule and Simpsons Rule. Anything else you see in this handout, it was written for the class in the spring, and I covered a little bit more with them than I'm planning to do with you guys because, you know, like I said, it's the summer. Everything moves really, really fast. Okay. So let's actually do this. So here for this question, we are going to, of course, ignore the thing that says midpoint. We're just going to do the trapezoid rule and the Simpsons rule just for you guys to see how it actually works out. And I'm pretty sure, yeah, we're also going to ignore this example. And we're also going to ignore that because you need to know about errors to talk about that. And we're also going to ignore this. We can really do just one example because This is actually going to illustrate everything you need to know for your test next week or whatever. So let's actually look at that. So here's an integral, right? We want to approximate the integral from 0 to pi of the sine function. Okay, so that's our goal. We're going to approximate it using 4 subintervals, and we're going to use the trapezoid rule as well as Simpsons rule. So let's actually get into that. So B. Just like with Calc 1, one of the first things you're going to want to do is you're going to want to find the delta x. So this is pi minus 0 over 4. So your delta x is pi over 4. So your find delta x is going to be the first step. Second thing you're going to want to do is find the xi. Now for this, personally, I like doing it with a picture. It's just nice to visually see it. So you start off with the 0, you end with the pi, and you actually dice this into 4 subsections. Now to get from one subsection to the other, you add the delta x, you add the pi over 4. So that's what I meant earlier by xi is a plus I delta x, where I is the number of this. So you add that, you keep adding the delta x to go from one subinterval to the other. So 0, add pi over 4, I get pi over 4. Add pi over 4 again, I get 2 pi over 4, or pi over 2. Add pi over 4 again, I get 3 pi over 4. Add pi over 4 again, I now get pi. So these are my guys. So this here, that's like my x0. This here is my x1. This here is my x2. This here is my x3. And this here is my x4. And so now we can apply the formula. 3, apply the appropriate formula. So in this scenario, in example B, we want to apply the trapezoid rule. So the trapezoid rule says the area is going to be approximately equal to the trapezoid approximation with 4 subintervals, but that is going to be delta x over 2 times f of x0 plus 2 f of x1 plus 2 f of x2 plus 2 f of x3 plus f of x4. That's just by going the formula. I know in the trapezoid rule, I want to double up on the middle terms. And now you just, you kind of plug that in. So your delta x is pi over 4. This is going to be f of 0 plus 2 f of pi over 4 plus 2 f of pi over 2 plus 2 f of 3 pi over 4 plus f of pi. And in our situation, our f is the sine function. So this is going to be pi over 8 times sine of 0 plus 2 times sine of pi over 4 plus 2 times sine of pi over 2 plus 2 times sine of 3 pi over 4 plus sine of pi. And I do expect you guys to know what all those values are. Sine of 0 is 0. Sine of pi over 4 is radical 2 over 2. Multiply by the 2, you just get radical 2. Sine of pi over 2 is 1. Multiply by 2, you get 2. Sine of 3 pi over 4. 3 pi over 4 is in the second quadrant. All students take calculus, so that's also going to give you positive radical 2 over 2 times 2. Sine of pi is 0. So this becomes pi over 8 plus 2 rad 2. Or you can sort of cancel these guys into the 8 to get 4. And so this is pi over 4 times 1 plus radical 2. And that is our approximation. Any questions on that? Okay. It's okay for now. All right. Yeah, so this is fine. Like pretty much all you need to know for these guys is this new formula. Your delta x is done the same way that you did back in Calc 1. Really, this is really almost like a Calc 1 topic there. You could have done it back there, but this wasn't in the syllabus back in Calc 1 for whatever reason. So now let's actually do C, Simpsons Rule. So the same thing, we're just going to do Simpsons Rule. So here's from start to finish, just going to show you what this guy would look like. So again, we're going to do delta x. This is b minus a over n. This will be pi minus 0 over 4. This will be pi over 4. Next thing I'm going to do is I'm going to look at my interval. This goes from 0 to pi. I know I want to dissect it into 4. It's pi over 4. Add another pi over 4, I get 2 pi over 4. Add another pi over 4, I get 3 pi over 4. Add another pi over 4, I get pi. So now, what I'm going to do is I'm going to plug in the formula. This is approximately equal to the Simpsons approximation with 4 subintervals. And it's an even number of subintervals, so this does actually work. This is going to be delta x over 3 times f of 0 plus 4 f of pi over 4 plus 2 f of pi over 2 plus 4 f of 3 pi over 4. Move the chat box out of the way here. Plus f of pi. So that's our guy right here. So this is going to just be pi over 4 over 3 times the sine of 0 plus 4 times the sine of pi over 4 plus 2 times the sine of pi over 2 plus 4 times the sine of 3 pi over 4 plus sine of pi. So this would be pi over 12, 0 plus 2 rad 2 plus 2 plus 2 rad 2 plus 0. So that is pi over 12 times 2 plus 4 rad 2. Or for this guy, it looks like pi over 6 times 1 plus 2 rad 2. That would be that. And so those are your approximation. And I mean, normally I would show the decimal approximation here, and I would look at, and I would show you what the actual answer is, and we can compare the decimals to see that the error formulas are actually working, but we're not doing them, so we don't know. Odd subintervals do not work for Simpsons Rule specifically. So the reason why is that here it has to be even for Simpsons Rule only, not for anybody else, but Simpsons Rule. And the reason is, to define a parabola, you need 3 points. So you actually need 2 subintervals per parabola. So when you're doing a bunch of parabolas, each of them needs 2 subintervals to draw the parabola on. So it means you're kind of doubling up on subintervals for each parabola. So yeah.
Professor,
was someone
for the
saying
question,
something?
like, you know, for the one with the last question, with the one with the, you know, integrate the sine x with the, you know, Simpsons rule, you know, from 0 to pi, like, you know, why isn't it like, you know, pi radical 2 over 3 plus pi over 6?
pi radical 2 over 3? Where did you get, where would that
Plus
come from?
pi over 6, like, because if you take a look, according to what you solve, you see 2 pi over 12, right? If you simplify, you get pi over 6. And 4 radical 2 pi over 12. That would be, pi radical 2 over 3.
Pi radical 2 over 3.
Plus pi over 6.
Oh, that's if you expanded it. You just multiply it out?
Well, that's what I got,
Okay.
just now.
It's
And switching to
exactly
the
the
other
same.
side.
It's exactly the same thing. You know what's funny about this though, is that there was a time when I would give the answer in this form and you always ask me to factor it. And now when the answer is in a factored form, you're asking me to expand it. I don't know how to make you happy, Jason.
Like, would that still be the right answer if this was like
They're both
multiple choice or short
the
answer?
same. There's no difference between these two values. They're exactly the same thing. One, you just multiply it out. The one answer is in factored form, the other one isn't. They're both the same. But that's funny. Before it was like you always wanted me to factor the answer, and now it's like, yeah. So unfortunately, these guys we don't actually need to know. Like what you need to know for this section is just what I did in that example. This is some stuff that I would have covered in the spring, but we don't need it. So we will stop there. That's all for this topic. It's just another way to look at approximations for integrals. And so whenever you, yeah, it wasn't so bad. It is ironic, Jason. Anyway, yeah. So this, whenever I want you to appreciate the following. Whenever you're plugging in some definite integral into like Wolfram Alpha or Symbolab or something, and it's impossible to actually integrate the thing, like you're plugging in the integral from 0 to 100 of x to the e to the minus x squared. That's impossible to integrate. However, if you plug that into Wolfram Alpha, it's going to give you an answer. And now you might wonder, how did it get that answer? Well, it did one of these approximation methods. And it pretty much does enough subintervals to tell you the answer accurate to whatever number of decimal places it actually outputs on the screen. Now, of course, for me to explain how it would do that, I would have to explain to you these error formulas, but we're not going to do that. So basically, Wolfram Alpha would have these error formulas built in. It will know how many subintervals to use to get the answer accurate to like 6 decimal places or whatever. And so when you plug in this integral, it's going to run in the background like a Simpsons rule or a trapezoid rule or a midpoint rule, depending on the function you're entered. And it's going to give you the answer based on it adding up perhaps thousands of subintervals to get a good answer for you. And so this is what's going on in the background. That's pretty cool. All right. So what we are going to do now is we're actually going to start chapter 10. The first 2 sections are very introductory. And so, again, it's not going to be a very complicated lesson. So it's going to be very similar to, in terms of level of difficulty. Like the integration section was like hard compared to what we're going to be doing for the next few. I will say this though. A lot of students have trouble with series, which we're eventually going to get into. However, really, they shouldn't. I think the reason why they have trouble with it is because it's so different from integration that they're used to thinking in a complicated way, so that when something is actually simple, their brain just stalls. And I see that from time to time, like a student just thinking too complicated. So the problem, even though it's easy, in their mind, it's hard. And so they mess it up. Don't fall into that. Remember what I mentioned in the last class. Difficult problems are just a bunch of simpler problems. And when it comes to series, it's going to be a lot simpler than integration. as long as you just look at it as something separate from integration. Don't look at it as complicated or hard. Just look at it for what it is. It's a different kind of thing. It requires a different kind of thinking. It's familiar in some ways, and I'll point those ways out. But for the most part, you're not going to need any really complicated calculus tricks for these guys. The tricks here are mostly going to be like algebraic-based kind of things. So we are entering the second phase of the class. So phase one was pretty much us learning about integration techniques. Now we're in phase two, where we're going to talk about sequences and series. These guys are so important. They're very important in mathematics and applied mathematics and engineering, all over the place. If math is being used in some application, series are there some way. Most of how your calculator or Wolfram Alpha does things is through series. There are times when you might do something by hand and you have these nice little math tricks. A calculator is doing it by series, right? So series are very important, and we're going to start learning about them. Now, before we do that, we're going to cover something called a sequence, sequences. Now, this is an important topic in its own right, but we are just going to learn enough about it to be useful for series. Series is really the main thing we want to get a handle on in this phase. But sequences are going to be very useful. So we're going to start from the basics, start from scratch. We're going to define these things from the ground up and just run with it. So we're going to start section 10.1. This is just the section titled sequences. So what is a sequence? There are some rigorous definitions, but a fuzzy definition will do. A sequence is just a list of numbers in a definite order, right? The numbers in this list are called the terms of the sequence, okay? So a sequence, probably should have underlined that. The terms of the sequence, right? Now, this is not the best definition, and it's not even the most comprehensive, but for our purposes, that definition is going to be good enough. It's a good enough definition. Examples. Here's a list of numbers: -1, -3, -7, -11. That's a list of 4 numbers. That is a finite sequence, right? So that's what I would call that. I would call that a finite sequence. Why is it a finite sequence? It's a list. It's in a definite order because in my mind, when I was writing down this list, I was thinking about something specific, and it's a list that eventually ends. The second list, 0, 1, 1, 2, 3, 5, 8, 13, ... The ellipses here indicate that the pattern continues. This is called an infinite sequence because it's a list that goes on forever. It will never stop. Now, sequences, and this notation kind of looks weird just by how it's typed. It's usually typed a lot smaller, like AN, and you'd write a little n equals 1 down here, and maybe something like an infinity up here, or you might write something like AN, and you write a little n equals 1 up here, and you might write a 5 up there in case your list has 5 units, list is length 5, or so on and so forth. So sometimes here, the AN can describe what the list is doing, right? And this is particularly the kind of sequences we care about. So it's a sequence that can be described by some sort of formula. So for example, the formula that is in the first example, can I scroll down? Yeah. The formula that is in the first example, I'm on this line right here, -1, 3, 7, 11, right? That is a sequence that has length 4, so I can describe it as A sub n, where n starts from 1, goes up to 4, and each an is given by this formula, right? So notice that A1, I can plug that in, right? Here I can plug in and find that A1 is actually -5 plus 4, which is -1. A2 is actually -5 plus 4 times 2, which gives us the 3, and so on. N represents it's a placeholder that tells you the number, the position in the list. So for example, A1, A2, the 2 tells you it's the second guy in the list. So A sub n represents the guy that's in the nth position. I typed that out somewhere else later. The second sequence, does anyone know what that sequence is? 0, 1, 1, 2, 3, 5, 8, 13. It's actually a very famous sequence.
Is it Fibonacci?
Yes, it is the Fibonacci sequence. It's a very, very important sequence. People geek out about this sequence all the time. It's connected to so many things. It's connected to the golden ratio and the perfect spiral. And there are so many things in nature that you can actually track by this sequence. Fibonacci himself was studying rabbit populations when he came up with this sequence. And it's just really amazing. And it turns out that chances are, if you have one of those quacks who try to prove the existence of God using math, this sequence is going to pop up somewhere, right? So it's a sequence that it's all over nature, and it's super, a lot of people geek out to it. It's called the Fibonacci sequence. This guy can be defined as we call it recursively. Okay, so recursive definition is just a sequence where you're told about the first few values, and then all new values are defined in terms of the previous values. So the Fibonacci sequence, for example, you can define it by telling someone the first two terms, and then you tell them to get all future terms, just add the previous two terms. So here, you'd start out by telling them, okay, it starts with a 0 and 1. The third term is going to be adding the 0 and 1, you get 1. If you add the two previous terms, the 1 plus 1 give you 2. The 1 plus 2 will give you 3. The 3 plus 2 will give you 5. The 3 plus 5 will give you 8. The 5 plus 8 will give you 13, and so on. And you add the previous two terms, gives you the new term. And surprisingly, that list of numbers is so ubiquitous, it's not even funny. It's crazy how ubiquitous it is. And you can track so many things by using this list of numbers. It is actually kind of scary. And yeah, I can see how it would get some people to believe in God, to be honest. So here, at least to prove using math, I don't know if you can prove something like that using math, but the people who do use this sequence. Okay, so that's all the sequence is. It's just a list in a definite order. There is some formula. Usually in a math class, we are thinking of some specific formula in our heads when we're writing down the list. And that's all that is. A sequence is just a mathematical, a list where there's some sort of mathematical underpinning. It has a definite order for the guys in the list. As I mentioned here earlier, the subscripts actually tell you about the position of the guy in the list. So a sub 1 tells you that it's -1, a sub 2 is 3, a sub 3 is 7, a sub 4 is 11. So the subscript actually tells you the guy that reaches out in the certain position. So a sub 7 is just the 7th guy in the sequence. Another way to think about sequences is as functions. So we can think of a sequence as a function where the input set is the set of natural numbers, just the counting numbers, 1, 2, 3, 4. And the output is the value, is actually the terms of the sequence. So here I drew a table for the Fibonacci sequence, right? So that it's 0, then 1, then 2, then 3, then 5, right? So you can think of it as the input is 1, the output is 0. Then the input is 2, the output is 1. The input is 3, the output is 1. The input is 4, the output is 2, so on. And I can talk about this in terms of some function. F of 1 gives me the 0, f of 2 gives me the 1, f of 3 gives me the 1, f of 4 gives me the 2, and so on, right? So I can kind of think of this as a function that only works on the positive integers, and that's one way that's useful. And when it comes to that version of looking at sequences, you can get a couple important mathematical concepts out of that. The concept of convergence and actually sketching a sequence. So let's talk about convergence of a sequence. If I can think of a sequence in terms of a formula and a function, I can consider the limit of that function. We can say that an infinite sequence, this doesn't work for a finite sequence. We say that an infinite sequence converges to a number L if the limit of that sequence as n approaches infinity goes to L. If no such L exists, we say the sequence diverges. Right, so that's defining the phrase diverges. This includes the case if the limit goes off to infinity or it does not exist. So yeah, I can talk about a sequence. It's just a list in a special order. I can name a sequence such as a sub n, right, the sequence of a sub n, and I can talk about whether or not that sequence converges. When I talk about convergence, I just mean I'm looking at the limit. Now, it's always going to be limit as n approaches infinity. So once you know you're in the context of sequences, the limit is always going to be as n approaches infinity. And so there are times when we're talking about sequences, we might actually leave off the little n approaches infinity part because it should be obvious to the reader that we mean that. We also have this notation. We can just write an arrow, an approaches L, to mean that the sequence converges to L. So we can do that. Okay. Now, the graph, how to actually sketch a sequence, I'll illustrate as we go through these examples. So let's look at some examples here. Determine whether the following sequences converge, and if so, to what? So here I just defined a few sequences. We're going to look at whether they converge or not, and just to actually draw some pictures as to what it would mean. So let's do the first example. I'm going to do it for you guys, and you guys can help me with the others. So here's a sequence. The sequence n goes from 1 to infinity. It's defined by n equals 1 over n. So this is defining a list, right? So here's a list that's in a definite order, right? So this is defining, this is the list. The first term is 1 over 1. The second term is 1 over 2. The third term is 1 over 3. The fourth term is 1 over 4. So here's a list that is in a definite order. I know how to find all the guys in the list. What does the 100th guy looks like? Well, he looks like 1 over 100. And I can continue, right? There's a definite order in my mind in how I'm writing out this list. It is given by this formula, an equals 1 over n. Now we can ask the question, does this converge? So whenever someone asks you, does a sequence converge? What you immediately do is you want to find the limit of the sequence. And again, I can omit the n approaches infinity because it's always going to be that. And when I draw the picture, you'll see why. Can omit the n approaches infinity part because it's obvious for a sequence. It's always as you approach infinity.
Professor, like, if you were to solve this problem, this is about like sequence and Fibonacci series, and also about like finite series or infinite series. If you were to determine whether or not if it converges or diverges, I would say converges because 1 over infinity, if you do the division, like you would get 0, and when you get 0, it converges to 0.
Exactly. So here, an converges to 0 would be the answer. So yes, it converges. In fact, it converges to 0. Yeah, Jason, I know that's what I said. That's why I said yes. I was agreeing with you.
Not with you, but with the other students.
It's funny sometimes Jason says things and I and I agree with him, and then I say it myself and he's like, that's what I said.
No, I wasn't talking with you. I was talking with the students.
Oh, so Jason was addressing my students. Okay. So this one does converge, and that's as easy as it is. You just take the limit. Of course, what this means is you guys have to remember all your limits. We knew that from last class, actually. So yeah, so by the way, Jason, when you actually speak, they actually do hear you, so it's okay. All right, so this sequence does converge. How do I know? Well, I took the limit and I got a real number. So that's it. It converges to 0. That's it. All right, let's look at another example. What about this one? Oh, I wanted to do the other thing. I actually wanted to sketch this out for you. What would the sketch look like? So here, I can think of this as a function, which kind of gives you the idea that I can maybe draw a sketch of it. Let n be on the horizontal axis, and let a sub n be on the vertical axis. Notice that when n is 1, the a n is going to be also 1. Then I can plug in n equals 2. Then the a n is going to be a half. Then I can plug in n equals 3. The an is going to be a third. Right? Da, 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 and so on and so forth. Like when I plot this guy, you'll notice that it's a bunch of isolated dots. So this tells you two things. One, I can't find the limit as n approaches anything else. So for example, the limit as n approaches 2 wouldn't make any sense. Note, for example, limit as n approaches 2 of an makes no sense, because you can't get arbitrarily close to 2, right? Can't get close. There's a chasm between 2 and the next guy. Limits are all about getting close, arbitrarily close. I cannot approach the point 2. It's an isolated point. There's nothing to the left or to the right. So you can't get close. However, what you notice is I can talk about the trend. I can talk about the fact that I can kind of imagine that there's some curve connecting these guys. However, the trend goes to 0. It keeps getting smaller and smaller, but it approaches 0. This is the convergence. If you realize that it's trending somewhere, you can track that with convergence. So I can't talk about the limit in any intermediate stage, but I can talk about the limit going off to infinity. And essentially what I'm doing is I'm talking about the trend of this sequence. How is it behaving in the long term? Okay. So that explains simultaneously how you can actually sketch a sequence, as well as why limit as n approaches infinity is the only sensible limit to actually talk about. It doesn't actually make sense to talk about any of the others. So it's always limit as you approach infinity. And so I can be a little lazy here and just write LIM when I'm talking about a sequence, because you can't say limit as you approach what? It's a sequence. It's always approaching infinity all the time, every single time. What about this one? The sequence defined by an equals n. Does that converge? Well, question for you guys, does this converge? No. Well, let's see. What we will do is we would find the limit. Find the limit of an. This is just the limit of n. That is, of course, infinity. This means an diverges. Because there is no real number that the limit approaches. We can actually sketch this out as well again, plotting n versus a sub n, thinking of it as a function. When your n is 1, it's at 1. When your n is 2, it's at 2. When your n is 3, it's at 3. And again, you look at the trend of that guy. What is it going towards? It just keeps getting bigger and bigger. The trend goes off to infinity. It's not going to settle at any number. It diverges, right? So yes, we call this trend linear, but that's not the important thing for us. I'm not really going to have you identify what kind of trend it is. That's more something that's more important for statistics. For us, I just want to know, does it settle at some number, or does it go off without bound to infinity or minus infinity, or does it diverge? So this guy here diverges. Here's another one, and this is a very important kind of expression. So this serves as an example as well as an introduction to this kind of expression. Minus 1 to the n. I want you guys to notice what this guy would look like. Notice here, if you look at this list, the first guy, when you plug in n equals 1, you're going to get minus 1. Then when you plug in n equals 2, you get minus 1 squared, which is plus 1. Then you can plug in n equals 3, minus 1, then 1, then minus 1, then 1. right? So this, notice, signs alternate. And this is very important. We'll be using expressions like this in the future. To indicate alternating signs in the future. Okay. So that's what that guy behaves like. Now, what would the limit be? If we look at the limit of an, that's just the limit of -1 to the n. And what's that? Well, that's just dne. Not that it goes to infinity or negative infinity. It actually doesn't go to anything. It bounces up and down. So in this case, an also diverges. It does not approach any real number. And if I were to actually draw a picture of what this guy is doing,
Jason.
At 1, it's at -1. At 2, it's at +1. At 3, it's at -1. At 4, it's at +1. So it bounces up and down. It oscillates between two values. It bounces up, down, up, down, up, down, and it does this forever. Again, does not settle at a number. The overall trend isn't anything. Sometimes it's at 1, sometimes it's at -1. So the limit does not exist, and therefore we say that the sequence diverges. I would not call this harmonic. The word harmonic is actually used for something special. So in math, in sequences and series, harmonic actually means something very specific. I haven't introduced that yet, but I will at some point. It's a very, very important concept. And it's a concept that we usually apply to series. And it's a series that has to do a lot with auditory processing and actually like sound waves. It comes up all the time, which is where the name harmonic comes from. It's very harmonious, but we will get to that at some point in the future. There's another one. We're not going to illustrate this one, but just tell me about the limit. So what do you guys think about this one? Does it converge? What do you guys think? First of all, do we know what this symbol means? The n with the exclamation point?
Factorial, of course.
Right, n factorial, of course. That's what it is, right? So whenever you see an exclamation sign in mathematics, it doesn't mean the person is shouting at you. It's not n, it's n factorial, right? So for those of you who haven't seen it, let me just give you a definition. This is equal to 1 times 2 times 3 times all the way up to n, where n is a positive integer. There is a way to define this guy in general. However, that's above this class. That's above our pay grade. And we define, by convention, 0 factorial as being the number 1. So in general, that's the definition. So for example, if I say 5 factorial, it's not me shouting 5 at you at the answer. It's me saying 1 times 2 times 3 times 4 times 5. And that's actually 120. Yeah. So you can't say n loudly. When you put n exclamation point, it means factorial. I suppose if a math person wants to shout, they have to put a double exclamation point. And then everyone's going to think, geez, math people need to learn how to control their emotions. They're going overboard. No, it's because one exclamation point actually means something very specific to a math person. Okay, so that's what it means. So now that you know that, what about this guy? Does it converge? What do we think? No, Abdullah, bravely, he takes a stand. Well, let's consider it. So if we look at the limit of an, it's just the limit of n factorial over n raised to the nth power. Now, it's hard to actually look at that. What we can do here, though, how do we actually even know how to take the limit of a factorial? What does that even mean? However, if we write down the definition, and below it, we write down the definition of n to the n, which is like n. So when n is large, notice that it's going off to 1. However, for a smaller n, as n approaches infinity, these guys are all going off to 0. So you have a bunch of zeros multiplied by 1. Essentially, you get the limit is 0. So here, it actually does converge. It turns out that an converges to 0. Yeah. You win some, you lose some, Abdullah. Just brush it off and try again. This actually illustrates something from limits, something that you learned in Calc 1. Remember, and I don't remember if I mentioned this to you guys already, but remember how logs are much smaller than polynomials, which are much smaller than exponentials, which are much smaller than, well, factorials. So I mentioned this to my Calc 1 class. Some of them didn't know what a factorial is, so now you guys know what we're talking about, which are much smaller than guys like this. So this was a list that was very important that came up in limits, where you know that guys on the right are huge compared to guys on the left as you approach infinity, right? So that was the rule that we're talking about. And again, this is a Calc 1 thing, so I'm not going to elaborate on this too much, but that was the idea. So we know, for example, if I'm taking the limit as n approaches infinity of a raised to the n divided by n to the a, I know it goes off to infinity. If I'm taking the limit of, say, n to the a divided by n factorial, I know it's going to go off to 0, because the guys on the left are so big compared to the guys on the right that the guys on the left are effectively 0 as you're approaching infinity. So compared to the n to the n, your n factorial is like a 0. It's almost like you have a 0 divided by infinity. And so that's going to actually go to 0. So this ratio, as n is going off to infinity, gets very small because the denominator is getting huge compared to the numerator. Here are some other things. Properties of convergent sequences, meaning these guys do not hold if your sequence don't converge. So if you take the limit and you don't get a real number, forget everything in this list. You have to verify on a case-by-case basis. However, if they do converge, then all of these nice little limit properties that you're used to actually will work out. The limit of a constant times the sequence is a constant times the limit of the sequence. The limit of a sum is the sum of the limits. The limit of a product is the product of the limits. The limit of a division is the division of the limits, provided you're not divided by 0. The limit of a sequence to a power is the limit of the sequence raised to that power. And all of that still works out. And yeah, those are just some properties that we now know. So a sequence is just a list written in a definite order. We can talk about that list converging. Basically, this means we can take a limit of the terms and it approaches some real number. If this does not happen, it will diverge. We need to remember all our rules from limits to be able to do this. So again, everything you learn from limits is going to be important. including indeterminate forms and L'Hopital's rule, squeeze theorem, limits at infinity of rational functions. All your limits, you need to review it. One more thing I want to talk about here is that what it means for a sequence to decrease. This just means each new term is smaller than the previous term. And if you can differentiate the formula, it leads you to say that A prime is less than 0. Hello? Okay. These are just some other statements that you might see in your homework, so I decided to define them. And that's it. That's all you need to learn about sequences. Pretty easy, right? That's section 10.1. Yeah. Okay. So the highlights, sequences just listed in definite order. We mostly care about infinite sequences, and they're the only ones we can talk about convergence because these guys can't approach infinity. Sometimes you can write the sequence as a formula, and this is when it's.
This is called.
Hello? I think someone has left the mic on. Hello? I'll mute him. Okay, there, silence. Okay, yeah, so that's all it is for sequence. Convergence just means that the limit approaches a real number, and the limit, you just take it how you remember taking limits from Calc 1. Divergence means it doesn't approach a number. These are the properties of limits that you can assume works with sequences, and this is what it means for a sequence to decrease. Okay. Now what we're going to do is, again, we're keeping things very easy. We're just doing some intros here. We're going to introduce what a series is. Yay! Okay. And I'm going to motivate it in what I think is a very interesting way to motivate this. How do you actually start talking about series? Where do I begin? Was the best of times, it was the worst of times. Okay, so back in the day, philosophers were, it was a big thing to be a philosopher, right? So how guys today, they go to a bar, they try to pick up girls, and they're like, I'm a doctor, I'm an engineer. No, back in the day, you used to go, hey, babe, I'm a philosopher. Like it was a big deal, right? Everyone was into philosophy. Either that or they were into like pillaging other villages or whatever, right? So philosophy was a big thing. And now it's, there was this dude called Zeno. And Zeno was a guy who came up with a bunch of paradoxes. I believe they speculated that in the Library of Alexandria, there was a book of Zeno's paradoxes, and there were like 40. But like a few of them survived till today. We lost most of them. However, one of the famous ones is the Dichotomy Paradox. This was a very famous paradox of Zeno. So this was posed like 400 BC. So we're talking about 2 millennia and change, 2.5 millennia ago, people were considering this kind of question. So the dichotomy paradox basically kind of says, it's very depressing if you think about it, but it basically says progress is an illusion, right? You can't move anywhere, you can't get anything done, right? Or that was the paradox. How does anything actually get done? So Zeno was like, you know what, to accomplish anything, you have to first accomplish a part of the thing, right? If you want to clean your room, you have to first get to a point where you've cleaned half the room, right? If you want to travel a mile, you have to first travel half of a mile. And then after that, you have to travel half of a mile. And then after that, you have to travel half of a mile. So if we go out and actually decide that we're going to walk 1 mile today, well, before we cover that, we have to cover half a mile. Then we're going to have to cover 1/4 of a mile. Then we're going to have to cover 1/8 of a mile. Then we're going to have to cover, and you end up with a situation like this, right? So in order to cover up a mile, you have to cover a half plus 1/4 plus 1/8 plus 1/16 plus ... to cover the mile. But this means to cover a mile, you have to cover an infinite sum of portions of a mile. How does anyone ever have to cover up a mile? They'd have to be able to add up infinity, right? So this was the paradox. How do you actually walk a mile? Can it actually be done? The mathematical viewpoint of this paradox is, does the sum 1/2 plus a quarter plus an eighth, does it have any meaning? That is what we're going to talk about today. It turns out that to talk about Zeno's paradox, why it was so bafflesome to people 2.5 millennia ago, is it involved the idea of an infinite sum. Now, another name for an infinite sum is an infinite series. So an infinite sum, we call an infinite series. So a series is just a sum. It's just another word for sum. That's all it is, right? So this is a very important thing, an infinite sum, knowing how this sum actually works out, right? And we've seen examples of this, right? Back in Calc 1, when we were learning about an integral, what was it? A Riemann sum. We had to add up an infinite number of areas of rectangles in order to create an integral, right? So this is actually a very, very important idea. We need to be able to add up a lot of things, an infinite number of things. This is where a series comes into play. In the case of the integral specifically, there was a shortcut to adding up these infinite sums. It's called the antiderivative and the fundamental theorem of calculus. However, in general, we want to talk about this in general. Is there a general way to think about infinite sums? Is there a general way to add up infinite sums? What if it's not connected to areas under a rectangle that has a nice formula associated with them? Can we still talk about them? So this is how we'll start to look at Zeno's paradox from a mathematical point of view. So here's how we're going to define it. A series is the sum of the terms of a sequence. So here I'm defining a series. So given this should be sequence. Which means I should probably change that, or I'm not going to remember. Okay. End intermission. Given a sequence AN, we just spoke about what that is, there is a corresponding sum. Just add up all the guys, A1 plus A2 plus A3 plus going on forever. To write that notation, we write this. We write sigma. This is like the analogous Greek letter S, uppercase S, right? Whenever you write that symbol, it means you're adding A1 plus A2 plus da-da-da, right? You would have seen this notation before, I believe, in Calc 1, even though you might not have emphasized it too much. So that's what a series is. It's just the sum. It's the sum of the terms of a sequence specifically is how we are going to think about it, right? Now, you can have a finite series, so something like this, the sum from 1 up to k of an, and it just means the sum eventually stops. However, we care about the infinite series. Also, when we're writing down a series, these guys here are called, this is called the index. Almost no one says that, though. They might call the limit of the series or whatever. But if you see the phrase index, that's what it's referring to. It's indexed by I. So an. So you write that symbol, it just means you're adding up terms that are defined by some sequence. So there's a very specific list that you have in mind, and you're adding up the members of that list. Now, how do we make sense of that? How do we actually add up the members of a list, especially in the case that the list is infinite? Well, again, let's go back to basics. Remember, every hard problem is just a smaller problem. Think of how you would add up a smaller list, a finite list. If you told a child to add up the numbers 1, 2, 3, 4, 5, how would they do it? Maybe with pebbles, right? And they would do it cumulatively, right? So you wanted to add 1 plus 2 plus 3 plus 4 plus 5. What do? You add them 2 at a time, right? You add the 1 to the 2, and then you get a 3. Then you'll add a 3 to that. Then you'll get a 6. Then you'll add a 4 to that. Then you'll get a 10. Then you'll add a 5 to that. Then you'll get a 15. You can add successively, right? And you can do this for finite sums. However, if to bring this back to math, what you can think of this as doing is you're creating a sequence, actually. You're creating a sequence that adds up all the cumulative sums. So for example, you can think of the number of terms of being added as the placeholder in the sequence. What is the sum so far? Well, after I add one term, it's 1. If I add 2 terms together, it's 3. If I add 3 terms together, it's 6. If I add 4 terms together, it's 10. If I add 5 terms together, it's 15. I can add this up. Notice that I can think of this as creating a sequence over here, S sub n, where my S sub 1 is 1, my S sub 2 is 3, my S sub 3 is 6, my S sub 4 is 10, my S sub 5 is 15. This kind of sequence, a sequence used to track these successive sums, it's called a sequence of partial sums. That's what this guy is called, right? That leads to this definition here. If you have a series AN, a sequence of partial sums is a sequence defined by this equation. So it comes from when you take your Sn and you just add up the first n terms. So S1 is the sum of the first 1 terms. S2 is the sum of the first 2 terms. S3 is the sum of the first 3 terms, and so on. S sub 1000 is the sum of the first 1000 terms. So these are called the partial sums. And when you look at them as a sequence, you create a sequence of partial sums. Now here's what you will notice. Notice that the sequence of partial sums, the sequence approaches the final answer. The final answer to the sum here, I have to move this chat box out of the way. The final answer to the sum here was 15. But notice that I could figure out that it's 15 just by going along the sequence. Just follow it to the end. The end is going to tell me the answer. We want to generalize this idea to the infinite case. Basically, what we're going to do to add up an infinite sum is figure out what is the sequence of partial sums and look what it's going towards. In other words, look what it converges to in the sense that it's infinite. So in the case that I have an infinite list, I can create an infinite sequence of partial sums, check what it converges to. If this converges to a number, then I define that to be the sum of the series. This is the sum of all the terms of the sequence. This leads us to the following concept. We say a series converges to a real number S, and we can say the series is the number S if the sequence of partial sums converges to the number S. In all other cases, we say that the series diverges. Okay? Let's actually use this to figure out Zeno's dichotomy paradox, right? It's better late than never, right? 2.5 millennia later, let's actually figure out, can we actually walk a mile? Is it possible to actually add these numbers together? Well, let me illustrate to you how we're going to do this. Well, we'll start by constructing a sequence of partial sums. So we can start with S1, that's a half. S2, that will be a half plus a quarter. In other words, that's going to be 3/4. S3, that's a half plus a quarter plus an eighth. That's going to be, well, that would actually end up being 7/8. And you can actually continue with this list. Now, what would the nth term look like, Sn? So here, you might want to come up with some sort of general formula to distinguish this sequence here. Here's what you should notice. The denominators always look like 2 to a power. And the numerator is always going to be 1 less. This, notice here, this is 2 to the power 2 minus 1 over 2 to the power 2. This here is 2 to the power 3 minus 1 over 2 to the power 3. And so on. In fact, I can get that my Sn is going to look like 2 to the power n minus 1 over 2 to the power n. You can actually figure that out. Let's actually write this out a little bit more. So this would look like 1/2 plus 1/4 plus 1/8 plus dot, dot, dot. Going up to the nth term, it's 1/2 to the n. That is going to equal to this formula. And so now, if I look at if I call this series the sum of an, where an just looks like, 1/2 to the n, I can think of that as the limit of the partial sums, the sequence of partial sums. This is going to be the limit of this expression, 2 to the n minus 1/2 to the n. And what is that limit? Just to see if we remember our limits. Limit as n approaches infinity of 2 to the n minus 1 all over 2 to the n. No. Let me help you out a little bit. I can simplify this a little bit. This is actually 1 minus 1/2 to the n. Right, now as n approaches infinity, what does that go to? It goes to 1. What do you know? We actually walked 1 mile. It turns out that walking a 1/2 mile, then a 1/4, then an 1/8, then a 1/16, then da da da. How much would you cover if we could dissect this an infinite number of times? You would cover 1 mile. We can actually walk 1 mile. Turns out things do get done. You ever have that feeling that your life isn't going anywhere? Well, math is here to tell you that that's not true. We can actually get somewhere. We can cover the mile. Zero's paradox is not a paradox. We can add up an infinite number of numbers, and it can make sense in the real world. Of course, it has to make sense. We travel miles all the time. If we had to cover an infinite sum to travel a mile, then it must be possible to to have an infinite sum have meaning, have real, tangible, mathematical, and otherwise meaning. And by going through this process, we end up with a meaning that makes sense in this context. And we can end up with a meaning that makes sense in any context. Right. So now that is what it means for a sum to converge. Of course, this process here is very complicated to do in general. And so we're going to want a nicer way to look at sums in the future. But this is just illustrating the idea from the basic fundamentals, from us building up what it means to be an infinite sum and what it means to actually add up an infinite number of things. This is how you do the problem. However, for this particular kind of sum, we're going to see many ways to actually find the answer in the future. So turns out we can walk a mile. And boom, boom, boom. Now, here's something I want to talk. I'll probably talk about this concept. And these are just some properties as well. So they follow certain properties, the series. But what I'd like to talk about is another important concept of convergence of a series. So remember, a series converges when someone says that this infinite series converges. Basically what they're saying is that this infinite number of numbers, they add up to something meaningful in the real world, right? So I can add an infinite number of numbers and it actually has some meaning attached to it. I can write down an answer to this infinite sum, right? So it turns out though, that there are several ways, there are several kinds of answers that you can get from adding an infinite sum and several kinds of convergence. So here, given a series, right? Let's make sure I actually paste everything. Given a series an, right? It's just an infinite sum. If the series of the absolute values, right? So I put absolute values around all the terms and I add up all those terms. If that new series converges, we say the series converges absolutely. Meaning it converges with absolute values around all the terms. If the series converges without the absolute values, but when you put absolute values, it does not converge, we say it converges conditionally. So there's a difference between converging absolutely. This means you converge even if you put absolute values around all the numbers, versus converging conditionally. And we're going to see examples of both types of series. There are series that converge in various types, right? Now, if a series does not converge absolutely or conditionally, of course it diverges, but there are two types of convergence for series. You can converge absolutely, or you can converge conditionally. Now, why is it important for us to think about convergence in these two ways? It might seem odd why we're thinking about this, but it turns out that there's a very important theorem that tells us why we need to worry about this. It's called the Rearrangement Theorem. So Riemann, for his PhD thesis, the same guy who came up with the Riemann Sum, which is why we do calculus the way we do it now, that guy, when he was defining the Riemann Sum for his PhD thesis, it was a paper that was about 100 pages long. It turns out on one of those pages, he kind of proved a theorem on the side, like, oh, by the way, this is actually true as well. There's something I'm going to call the Rearrangement Theorem. Here is what he said. Let AN be a series that converges conditionally, right? And R is any real number. Now here it is. Now this is going to be really crazy when I say this, so hold on to your seats. If the series converges conditionally and R is any real number, then it's going to be possible for me to rearrange the order in which I add the terms in such a way that the series can add up to R. Literally anything. If I have a series that converges conditionally, pick your favorite real number and tell me, I can rearrange the terms so that they add up to that favorite number. I really like the number e to the pi. If you give me a conditionally convergent series, I can rearrange the terms so that they add up to e to the pi. I can get them to add up to 1. I can get them to add up to 100. I can get them to add up to minus 15. I can rearrange terms to add up to whatever I want. In fact, I can rearrange terms and get it to diverge. I can rearrange terms and get them to add up to infinity. I can rearrange terms and get them to add up to minus infinity. Here's the thing though. If your series converges absolutely, that is not possible. If you have an absolutely convergent series, then no matter how you rearrange the terms, you will always get the same answer. In other words, addition is only commutative in the infinite case if you have an absolutely convergent sum. Remember when you're adding numbers 1 plus 2 plus 3? We learned that addition is commutative. You add those numbers in any order, it will always add up to 6, no matter what order. However, if you have an infinite sum, this very basic principle is no longer true. It turns out that you can rearrange the terms and get it to add up to something else if it's conditionally convergent. So what you can realize here is that absolute convergence is actually important. It tells us that we can still have commutativity of addition. This is important for many reasons, obviously, but it's important for calculus. We're going to get to the point where we're going to want to add up an integrate or differentiate an infinite number of terms. However, this equals, I can add up these guys. It only works only if the sum a1 plus a2 plus da 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 converges absolutely. Because I can rearrange the term and get a different value for the integral. The area under the curve is going to change. For calculus, we need absolute convergence. So a series can add up to something. However, if it adds up to something in a conditional way, it turns out you can rearrange the terms to add up to something else. However, if it's absolute, all rearrangements will add up to the same thing. This is a very important idea, and it's called the rearrangement theorem. Thanks to Riemann. So it's going to actually be important for calculus. Series have these two properties. We'll talk about that next time. But yeah, we'll stop there. That's the introduction to sequences and series. We're going to do more with these guys moving forward. So we'll do a lot different. We'll streamline the math a little bit more. Today was about just introducing you to the concepts, and hopefully it was insightful and interesting. But that's where we're gonna end today. So let's actually wrap up there, ladies and gentlemen. As always, I will post the video along with a PDF, and we will continue with that next time. Hope you enjoyed the lecture. We'll do more mathy stuff next time. We'll start to streamline this idea. Still, the concepts are a little fuzzy. The next few sections are going to be about us really learning how to add up series in various scenarios, and we'll start talking about that. Other than that, I will leave you guys to it. Have a good night. Stay safe. I will see you guys in the next one. You're welcome. You're welcome. Good night, everyone. And I'll see you guys later. Ciao.